Hello, I'm Dr. Maurice Dupre, and on this segment we're going to discuss the dot product of two vectors. We're going to look at it geometrically to begin with because the geometric viewpoint when dealing with vectors is really the way to look at things in order to solve problems effectively. So let's see how we can actually get the dot product of two vectors from a geometric picture. Here is a picture of two vectors, v and w. Now what I've done to begin with is drawn a line through the vector v. And so what I'm going to do is use this picture to define the dot product of v with w. So in this picture, this number line is going to have a scale so that the tail of v is at the 0 point on the number line, and the tip of the vector v is therefore at the point corresponding to the number length v, which we denote with v surrounded by two double bars, a pair of double bars. Okay, so given that we've established this number line with the vector w represented so that its tail is at the tail of vector v, I drop a perpendicular from the tip of vector w down to this number line. So that's a right angle right there, and it will hit that number line at a point on that number line which will be represented by the number x. And so consequently, in terms of that picture, the dot product of v into w is length v times x. If I did it the other way, I'd put the number line through the vector w, and so again its tail is at the 0 point on this number line, and the tip of w would then be at the point which would have coordinate length w on that number line. And so consequently I would drop a perpendicular from the tip of v down to that number line, and that would correspond to the number y on this number line, and I could say w dot v is length w times y. Now why should those two things be the same? After all, we know the dot product is commutative. We would want that, and consequently what we have to do is see why from geometry are those two things equal. Well, notice this big triangle and this small triangle are right triangles. Not only that, they have an angle in common, namely the angle between the two vectors v and w. And consequently, what that tells us is these two right triangles are similar. So that means ratios of corresponding sides are the same. So let's look at the ratio of the hypotenuse divided by the short side for each one. For instance, if I look at the little triangle, the hypotenuse has length v and the short side has length y, so we have length v over y. How about the big one? Well, the hypotenuse is length w and the short side is x, so the ratio is length w over x. So if I cross multiply, that tells me length v times x equals length w times y, and tells me these two expressions are exactly the same. And so this way of looking at the dot product tells me that either vector can be used to drop a perpendicular from its tip down to the line through the other and get an expression for the dot product. Now the main use of this is by looking at the picture we can instantly see a lot of properties of the dot product. For instance, suppose w actually leans back this way, so you see in this blue vector I've pictured here, it kind of tilts back away so that the angle from v to the blue vector is more than 90 degrees. Well, notice on this number line, this point is negative because here's 0, that's the positive direction, and so consequently the x in this case would turn out to be negative. Length v times x would be a negative number, and that tells us if the vector's angular separation is more than 90 degrees, the dot product will be negative. Moreover, if vector v were to point perpendicular to v, when I dropped the perpendicular down to the line through v, it would hit right at the 0 point. X would be 0, and the dot product is 0. So that's one of the most useful properties of the dot product, is that when I take the dot product of perpendicular vectors, I get 0. So V dot W is 0 if V is perpendicular to W. Let's look at another situation. Suppose that W and V actually point in the same direction. So this W is actually along the same line here. Well, then the tip of W would be right on the number length W, and so in that case X would be equal to length W, and so V dot W would be just the product of the lengths. So we could say, for instance, coming right here, V dot W equals length V times length W if they point in the same direction, which I'll write this way. I'll make a parallel symbol, but I'll put an arrowhead on top to denote that they point in the same direction. Well, I'm saying this. In other words, when they point in the same direction, the dot product is just the product of the lengths. How about in general? Well, remember that since this is a number line here, if I put the axis perpendicular to it into the picture, we can transform or think of polar coordinates. And so let's look at the polar angle from the vector V around to W. Call that theta. In that case, we know this coordinate X on the horizontal axis is the hypotenuse, in this case length W, cosine theta. So we can say X equals length W times cosine of theta. And so that gives a general formula for the dot product, which I'll write up here. V dot W equals length V, length W, cosine theta, where theta is the angle between the two vectors. So you see the dot product of two vectors is really a completely geometric thing. It's totally defined geometrically, and it's due to the fact that its expression in coordinates, which we know how to calculate, is so simple that we can go back and forth from geometry to calculations effectively. But to do that, you have to have a very good handle on the geometric meaning of this dot product. Now let's look at another picture which illustrates the way this works. For instance, here I've got a number line, and imagine that that number line is just going any direction in space, except that we've got a vector u here, which is parallel to that number line. So now what I want to do is imagine that I've got two vectors v and w, and they're anywhere in space, but I want to look at their sum. So we'll add them head to tail. V, W, here's tail of W at the tip of V, and so then we connect tail to tip to get the sum. That's our simple geometric picture of the sum of two vectors. So what I've done is I've imagined three planes. This first plane is perpendicular to the line L, and in it we have the tail of V and also the tail of V plus W. The second plane, also perpendicular to the line L, has the tip of V, and then we simply construct the third plane, also perpendicular to L, to contain the tip of W, which is the same as the tip of V plus W. And now what I've done is in those planes, I've dropped perpendiculars to the line. In other words, the whole plane here is perpendicular to line L, and consequently any line in that plane is perpendicular to line L. So connect the tip of the tail, rather, of V and V plus W to the point where the line intersects the plane. Likewise here and here. So the vector u is parallel to L, and so what we're going to do is simply put a number scale on that line L such that the length of u is represented as in terms of that unit. That is, the length of u here, if I take that length and put it on that number scale, comes out to the number length u on that number line. Okay, so in terms of that, what would be the dot product? Well, now u dot v is the length of u times that difference. It's just a shifting. So we've got the projection of both those points down to the number line, and so x2 minus x1 multiplied by length u is u dot v. Likewise, let's do that for the vector w. So u dotted into w will be length u times x3 minus x2. What about what we do that for v plus w? U dotted into v plus w will be length u times, where's the tip project to? X3 minus the x1. Well, notice what happens if I add these two things. The length u's factor out, and when I add this to this, here's a x2 and a negative x2, they cancel out, and I'm left with x3 minus x1, exactly this. In other words, u dotted with the quantity v plus w is equal to u dot v plus u dot w. That's the distributive law for the dot product viewed completely in terms of geometry. You should look at this picture carefully until you completely understand where all these lines are going, and in that way you'll get a very good geometric understanding of the way the dot product works. One thing we can do with the dot product of vectors is develop a way to compute the projection of one vector onto the line through another. Let's look at the picture of how this works. Here is the vector v, and I've drawn the line through vector v. And here's the vector w in space, skewed any old way we want, pointing through space. And so what I do is I put planes perpendicular to the line L and slide them in till one touches the tail of w and the other touches the tip of w. So any line in this plane is perpendicular to L, any line in this plane is perpendicular to L, and therefore perpendicular to the vector v since it's in the line L. Okay, so now what I've done is I've constructed the line in this first plane from the tail of w down to the piercing point where the line L pierces the first plane. And so that line is perpendicular to L. And likewise, I've done the same for the tip of w in the second plane. Now, the next step is to construct a parallelogram using this line and the line L, this segment from the two piercing points. Notice when I do that, I do it by simply taking a line parallel to this one and coming off this piercing point back up here. And now that gives me another point in this plane, and so I'll construct this arrow from the tail of w to this point, and I'll call that w2, and then I'll construct the arrow from this point over to the tip of w, and that's called w1. So this figure is a parallelogram, and that means this arrow w1, that vector, is parallel to line L, and therefore it's parallel to the vector v. On the other hand, the arrow w2 lies in this plane, which is perpendicular to L, and consequently every arrow in this plane is perpendicular to v. So w2 is perpendicular to v. So to summarize, w1 is parallel to v, w2 is perpendicular to v, and notice they're just going head to tail here, so w1 plus w2 is w. So what I've done here is I've broken the vector w up as a sum of two vectors, one of which is parallel to v, or parallel to the line through v. The other is perpendicular to the line through v, and therefore perpendicular to v. What does this mean? Well, w1 parallel to v, w2 perpendicular to v, and w equals w1 plus w2. First off, v dot w2 has to be 0 because w2 and v are perpendicular. What happens if I dot v with w? V dot w is v dot w1 plus v dot w2, but that's 0. So v dot w is the same as v dot w1. This will enable us to see what the projection of w on v has to be. What we do is we set w1 equals to w dot v times v divided by the length of v squared. Notice this is parallel to v. Why? Because this is just a scalar and it's multiplying the vector v. So in effect, we've written down a vector which is obviously parallel to v. Now, it may not point in the same direction because this dot product could be negative. So that's w1, and so we set w2 just to be w minus w1. Now let's notice that these things that we've stated right here are true. Well, the w1 by definition is already parallel to v, so what about w2 being perpendicular to v? Well, let's calculate v dot w1 and see what we get. If I dot v with w1, well, notice, dotting the vector v with this expression, just this is a scalar times v dot v. So we would get w dot v times v dot v divided by length of v quantity squared. But remember, the length of v squared is v dot v, so those cancel, and so what we're left with is w dot v. So that verifies that v dot w equals v dot w1. v dot w1 equals v dot w. So that property is satisfied. Now what happens after setting w2 equal to w minus w1, let's dot v into w2 and see what we get. v dot w2 is v dot w minus v dot w1, but we just observed that these two are equal, so their difference is 0. And what do we know whenever we get 0 for a dot product? Right away we have to realize that means those vectors are perpendicular. So what we've done here, you see, is to break up the vector w into two as a sum of two vectors, one parallel to the line through v, the other perpendicular to the line through v. And so the formula we have is simply right here. The projection of w on v is given by this expression. So it's easy to compute in terms of dot products. You just w dot v times v divided by length of v squared. And that's all there is to it. Okay, now let's do some calculations with the dot product. Just to review, if v has the components v1, v2, v3, and w has components w1, w2, w3, then to calculate v dot w in terms of their components, that's v1w1 plus v2w2 plus v3w3. In other words, we just take their same components, multiply their same components coordinate-wise, and then add the results. This formula, which appears in and of itself to be rather meaningless, actually has all those geometric properties that we just discussed. And in fact, it's easy to see if you look at those pictures that this formula is a consequence. But in any case, let's use this formula to calculate v dot w, v dot v, length of v squared, and the projection of w on v, as well as the component of w perpendicular to v, if we specifically have v as the vector with components 2, negative 2, 3, and w is equal to the vector with components 5, 4, negative 2. So all we have to do is calculate. So for instance, to begin, v dot w, we multiply corresponding components and then add the results. 2 times 5 is 10. Negative 2 times 4 is negative 8. 3 times negative 2 is negative 6, and we want to add these results. And so 10 minus 8 is negative 2. Excuse me, 10 minus 8 is plus 2. Minus 6 is negative 4. What's the significance of the negative sign there? Remember, when the vectors make an angle greater than 90 degrees, then their dot product will be negative. How about v dot v? Well, v dot v is, in effect, the sum of the squares of components. 2 times 2 plus negative 2 times negative 2 plus 3 times 3. 4 plus 4 plus 9. 8 and 9 is 17. Now, what about the length of v squared? Well, remember, the squared length of any vector is just its dot product with itself. And so we get 17. In particular, that tells us that the length of v itself is the square root of 17. All right, now let's do the next computation. We want to compute the projection of w onto v. So let's come over to a new board here and remind ourselves what v is. V is 2, comma, negative 2, comma, 3, and w is 5, comma, 4, comma, negative 2. And so the projection on v of vector w, remember, is w dot v multiplied by v and divided by length v quantity squared. Notice, in effect, this square, in a sense, is like 2 factors of v in the denominator, and up here I have 2 factors of v, and so in some sense the v's are sort of, but not really, canceling out, and we're getting something related to w. In fact, what we're getting is the projection of w on v. Well, we just calculated w dot v. It was negative 4. And we put down v, which is 2, negative 2, comma, 3, and divide by the length of v squared, which we calculated as 17. So to multiply negative 4 times this vector, remember, to multiply a vector by a scalar, just multiply each component by that scalar. So negative 4 times 2 is negative 8. Negative 4 times negative 2 is plus 8. Negative 4 times 3 is negative 12. That's all divided by 17. And likewise, to divide a vector by a scalar, just divide each component by that scalar. Remember, it's really multiplying by a 17th. So this is negative 8 17ths. Let me make that a little better. 8 17ths, negative 12 17ths. And so that's the projection of w onto v. Well, let's call this w1 for short. Once we've found the component of w which is parallel to v, or parallel to the line through v, to find the other component perpendicular, we just subtract this one from w. In other words, the perpendicular component, maybe I'll write it w with a perp symbol on it, is simply w minus w1. Well, let's calculate that. Okay, now we've computed the component of w that's parallel to the line through v, which I've denoted by w with the subscript 1 for short here, and it's negative 8 17ths, comma, 8 17ths, comma, negative 12 17ths. And so our final computation is the computation of the component of w perpendicular to v, and which I've denoted w sub little perpendicular symbol. That's w minus the parallel component, w1. And so that means at this point all I have to do is subtract this from this. Well, remember, to subtract one vector from another, you just subtract corresponding components. It's so easy. And so now w sub perp being w minus W1 is simply 5 minus negative 8/17. Well, that's 5 plus 8/17, or 5 and 8/17. 4 minus 8/17. And negative 2 minus 12/17. Excuse me, minus a minus 12/17. That would be plus 12/17. Okay, so we have 5 and 8/17, comma, and of course 4 minus 8/17 would be the same as 3 and 9/17. Remember, 8 plus 9 is 17. And then here, negative 2 plus 12/17. Well, let's see, that's the negative of 2 minus 12/17, and 2 minus 12/17 is 1 and 5/17. So we have negative 1 and 5/17 to finish off this calculation. And so there we have, in component form, the component of W, which is perpendicular to the vector V. So this completes our computation in this case. Well, let's look at a problem where we calculate work. One of the nicest applications of the dot product is to calculate work. Let's look at an example. An object is pulled 15 feet across a horizontal floor by a 100-pound force pulling 30 degrees above horizontal as shown. So here's the horizontal floor and here's the object. Maybe it's some kind of box full of heavy stuff, and we're pulling, but we're pulling slightly upwards. In other words, think of me trying to pull my son's toy chest across the floor by a rope, and I'm pulling, and I don't want to bend over all the way, so I'm pulling right from here, and the length of the rope is causing the angle to go down to the top of the box. So here we've got an angle of 30 degrees above the horizontal here. So what we want to do is calculate the work that we do to pull this object 15 feet with that 100-pound force. Well, the formula for work is very simple with the dot product. W equals F dot R, where F is the force that's applied and R is the displacement. That's the amount that you move as you apply the force. And W here, of course, is the work. So that means all we have to do is calculate the dot product of the force and the displacement. Well, where is the displacement in this picture? If we think of this as the starting position of the object, we're moving 15 feet, so the displacement is a vector R here, which in feet is 15 feet. And of course, notice force is in pounds, displacement is in feet, and so that means the units for work will be foot-pounds. So let's calculate. The force vector here is 100 pounds. The displacement vector is 15 feet in magnitude. These are magnitudes, and of course the picture shows the directions. And so we have to calculate the dot product of these two vectors. Well, remember our formula for the dot product. V dot W geometrically is length of V, length of W, times the cosine of the angle theta between the two vectors. There's the picture. So all you need is that angle between the two vectors. If you can find that, or if the geometry of the problem gives that to you, then this simple formula gives the dot product. So that's all we have to calculate. So what's the angle in this case? 30 degrees. So we need to calculate cosine of 30 degrees. Well, to do that, you might remember the 30-60 degree right triangle is half of an equilateral triangle, and so we can build it with an equilateral triangle, each side having length 2. This side, then the short side is square root of 3, Here's the 30-degree angle. And so the cosine of 30 degrees is square root 3 divided by 2. And so consequently, the length of our force is 100, the length of our displacement is 15, and we multiply that by the square root of 3 over 2. In other words, the work here is simply 1,500 square root 3 over 2. That's all there is to it. Well, we've seen how the dot product can be computed geometrically and with coordinates, and we've seen how we can compute work using the dot product. Remember, the geometric formula for the dot product often comes in applications. The dot product of two vectors is simply the cosine of the angle between them times the product of their lengths. So that's easy to remember. Well, now that you've seen these problems, why don't you try some on your own for practice?